Hello, Math 30-1 students. We're looking at applications of exponential functions practice. So we're going to go through a few different examples of the applications of exponential functions and then how they are useful. So we're going to look at the first example. A farmer's field has 1,800 mice. The population of mice increases 15% each year. Determine an exponential function that models the population of mice after t years. So we're going to start with this question here. So we know the present value, and we know that it's increasing by 15%. So I'm actually going to use the equation a equals p, which is our present value, 1 plus I to the power of n. So we know that we have our equation. It says determine an exponential function of mice after t years. So we can say a equals p, 1 plus I, so 1 plus 15%, so it's going to be 0.15 to the power of t, which is years. Now it says to the nearest whole number, determine the number of mice in the field after 4 years. So we're going to put t is equal to 4. So our present value, actually, we're gonna fill this in previously too. We're going to put the 1,800 mice as well. And we can simplify it as 1.15 to the power of t. So this is the exponential equation that I'm going to use for the next question. So our a is equal to, we're going to put 1,800, 1.15 to the power of 4. And then we're going to put that into our calculators. So 1,800, 1.15 to the power of 4. And you should get that there's about approximately 3,148 mice. So that's our answer. Round to the nearest month, how long it will take the population of mice to double. So we started with 1,800, and now we're doubling that, which gives us 3,600. So we know that the final amount is going to be 3,600, and we started with 1,800. And everything else stays the same, except we're solving for t now. So to start off, I'm going to divide both sides by 1,800. And that's going to give us 2 is equal to 1.15 to the power of t. Now I'm going to change this to logarithmic form. So I'm going to go t, which is our power, is equal to log. Our base is 1.15, so that becomes that little number, and our answer is 2, so this is how you rearrange the equation of a log. And then I'm going to go to alpha window 5, and I'm going to put that into my calculator. So alpha window 5, you're going to put 1.15 in the first blank and 2 in your second blank, and get the answer is, it's going to be approximately, because our answer, remember t represents years, we're getting 4.95 years, which is approximately 5 years. The question is, they want to the nearest month. So we're going to have to multiply this answer by 12 to get approximately 60 months. Okay, so that's our final answer there. Example number 4, use the following to answer the next 3 questions. So we have a newly married couple invests $2,500 in a variety of stocks. The annual average rate of return as a percentage is 6.5. So they want the exponential function describing the stock value in dollars over time. And we have the year since January 1st, 1989. So we're going to still use that same equation, a equals p, 1 plus I to the power of n. So we know that they're investing, our present value is $25,000. And the annual average rate of returns is 6.5. So we're going to go 1 plus 0.065. So that's taking this number and dividing by 100. And our n, which we're going to replace with letter t, is the number of years since January 1st, 1989. So this is our equation that we're using. And it's going to be v of t as well. So instead of a, we're going to use v of t just to show that we're using the right letters. Okay, so question number 5, it says, to the nearest hundredth of a dollar, what is the value of the stock on January 1st, 2002? So what we're going to do is first figure out how many years have passed since 1989. So we're going to have to go 1989 subtracted from 2002, and that's going to give us 13 years. So we now know that we're solving for v of t is equal to our present value, 25,000, 1.065 when we add the two numbers together to the power of 13. So we're going to put that into our calculator. And we should get that the value is now going to be $56,687.19. So our previous equation 2, we could have simplified as well to give us 1.065, just to shorten that a little bit. So that's a way of just simplifying our work. Example number 6, in what year will the stock be worth double the initial investment? So our initial investment was 25,000, so that means our value is going to be now 50,000. Okay, so we are first starting by dividing both sides by 25,000. So that gives us 2. Then we can change it to log form. So another strategy is putting log on both sides. And what that helps us do is it helps us put that t in front. So that's the power rule. T goes in front of log 1.065. And then we're going to divide both sides by log of 1.065. So log of 2, we're dividing by log of 1.065, and we get that it is 11 years. Now the question is saying in which year, in what year will the stock be worth double? So we actually have to figure out what year that's going to be. So we actually have to take 1989 and we have to add 11 years to that. And that's going to give us the year 2000 as our final answer. Now in this case, we're given the graph. They're saying, how long will it take for only 2 milligrams of the isotope to remain in the patient? Well, we need to find the equation. So whenever we write an equation from a graph, I always like to start with AB to the power of T over P. So we know A is actually the y-intercept. So we know the graph is actually starting from 10. So we have initially 10 milligrams. So it's going to be 10 multiplied by, here we're talking about a half-life. So we are losing a certain amount, or we're becoming half at a certain point. It says the graph shows the amount of milligrams remaining in the body over 24 hours. So we're going to go 1/2 when we're decaying to the power of T over. Now, when half the life has occurred, when we've reached half, It started at 10, and when did it become 5? Well, it became 5 at 6 hours, so that's going to be our half-life, or our doubling time. So in this case, our value of P is going to be 6 hours. So for it to go from 10 to 5, our half-life, we know that the value is going to be 6. So now we just need to solve for, it says, how long will it take until only 2 milligrams of the isotope remains in the body? So we are replacing our Y value with 2. And we're trying to solve for T. So we're going to start by dividing both sides by 10. So we get 0.2. And now we can put log on both sides. And then we can put that T over 6 in front. And we're going to divide both sides by log of 1/2. So put log of 0.2 divided by log of 1/2. And we should get 2.32. And then you're going to multiply both sides by 6. And that gives us, if we round to the nearest whole number in this case, T would equal 14 hours. Now, how long will it take for the isotope to metabolize, which is after 18 hours? So how much of the isotope has metabolized after 18 hours? They're giving us the T now in this case. So everything else stays the same. We're still going to have this equation y equals 10 1/2. T in this case is going to be 18, and we're still going to use the half-life of 6 hours. So 18 divided by 6 is equal to 3. So we can simplify that and then just put it directly into our calculator. So you're going to go 10 in brackets 1/2 to the power of 3. And you should get 1.25. So we know that we've used up 1.25 milligrams. So they're saying how much has metabolized. So we're actually going to have to take the original 10 milligrams and subtract 1.25 milligrams. So we're trying to figure out how much has been used or gone. And so we find that the answer is 8.75 milligrams has been metabolized. So the difference between our answer and the initial starting amount, which was 10 milligrams. To the nearest 10th hours, what is the half-life of the radioisotope? So we already found that. We actually needed those responses from the beginning. So our P in this case would have been 6.0 hours. So that's when we looked at our chart and we found out that when was it 5 milligrams? Well, we found out it was at 6 hours. And that was our half-life. Number 10. Janet invests $5,800 and earns interest at a rate of 6.7% per year, compounded quarterly. How long in years will it take for Janet's investment to triple in value? So we're going to use the value or the equation A equals P, 1 plus I to the power of N. So we know that she's investing $5,800. We know that she is getting interest at a rate of 0.067, but since it's compounded quarterly, we're going to have to divide this number by 4. And then our n is going to be in quarterly periods. Okay, so we're going to put that into our calculator. And we're just going to simplify the 1 plus 0.067 divided by 4. So we're just going to simplify a little bit before we go on. So we get that our inside here is going to be 1.01675 to the power of n. Okay, and then now we're going to put that tripling value would be that if you took $5,800 and you multiplied it by 3. So tripled value would have been, the A would have been 17,400. So we're going to start by dividing both sides by 5,800. So we know the answer is 3. Now we're going to put log on both sides. We're going to bring that power in front. And we're going to divide both sides with the log 1.01675. Now what we want to remember is that whenever we do this, this is the same as saying log, the base is that little number. So we actually can divide by that. Whenever we write it like that, this is equivalent to doing this. So this is what n is. So it's always log of your large number divided by log of that little base number. So in our calculator, we can go alpha window number 5, and we can put 1.01675 as that little number in the space, and then we can put 3 in that brackets, and then we can get our answer, which is n is equal to 66, but this means quarterly periods, 66 quarterly periods. So from this answer, we're still going to have to divide our answer by 4. So that's going to take us to approximately 16.5 years. And that's the answer they were looking for, was in years. Now we're going to go to applications of logarithmic functions. This is practice for it. So example number 1 here, we're looking at the measure of a telephone dial tone, which is 80 decibels, and the measure of original conversation, which is 50 decibels. How many times more intense is the telephone dial tone than an original conversation? So we're going to find out the intensity of one versus the other, and then we're just going to divide the answers. So we know that this one's going to be 80 decibels, and the other one's going to be 50 decibels. We're going to start by dividing both sides by 10. So divide both sides by 10, we get this, and now we can change it to log form. It's always going to be 10 to the power of our answer, which is 8, is equal to I. And here, 10 to the power of 5 is equal to I. And lastly, we're going to divide the two answers, the top one, which is the bigger one, over the smaller answer. So 10 to the power of 8 divided by 10 to the power of 5. And you should get that it is 1,000 times stronger. So we know that the dial tone is 1,000 times stronger than the original conversation. Seismologists measure the intensities of earthquakes at several different locations to find the epicenter. The magnitude of a certain earthquake at a point A was 6.2 and a magnitude at point B was 3.4. How many times more intense is the earthquake at point A compared to point B? So what we're doing is we're finding the intensity of one earthquake. What you want to remember is that it's going to be 6.2 is equal to log of I over I0, and the other one is going to be 3.4. Now we're going to change it into exponential form. It's going to be 10 to the power of 6.2 is equal to I over I0. And this one is 10 to the power of 3.4 is equal to I over I0. And then lastly, we're going to divide these two answers to get the comparison. So the higher number over the smaller one. And what you can always do is, same as in the previous question, you can actually subtract the powers whenever you have two bases dividing. So 6.2 subtract 3.4 gives us 2.8. So 10 to the power of 2.8 gives us about 630 times or 31 times if you round to the nearest whole number. So our answer is 631 times stronger. So when we compare two earthquakes, we know that point A is 631 times stronger than point B. Example number 3, an earthquake in city M was measured to be 102 times more intense than a city N. If the magnitude of the earthquake M was 5.8, then what was the magnitude of the earthquake in city N to the nearest 10th? So whenever we compare earthquakes, we can do this. 102 is equal to 10 to the power of the bigger earthquake, which was 5.8, minus the smaller earthquake, which is, we can say, the magnitude of city N. So what we're going to do first is put log on both sides. And then we're going to bring that power in front using the power rule. And then we can divide both sides by log of 10. So we're going to put log of 102 divided by log of 10 in our calculator and get 2 approximately. It's like 2.0086. And that's 5.8 minus m of n. And now in order to get mn by itself, I can subtract 5.8 here. And I'll get negative 3. It says to the nearest 10, so negative 3.8, which is equal to negative the magnitude of n. And then we're going to divide by negative 1 on both sides. So our magnitude at city N is going to be 3.8. And our last example, number 4, vinegar has a pH of 2.8, while lemonade has a pH of 3. How many times more acidic is vinegar than lemonade to the nearest 10th? So here, we're going to put 2.8 as 1 pH, And we're going to need to find the H plus, which is the concentration of the hydrogen ion for both. And then we can compare them. The other one, we're going to go 3.0 equals negative log of H plus. We're going to get the negative to the other side by dividing both sides by -1. So negative 2.8 equals positive log of H plus. Here, negative 3.0 equals positive log of H plus. And then we're going to change it to logarithmic or exponential form by going 10 to the power of your answer, which is negative 2.8, and that's equal to your H plus your concentration. So that's one concentration, and then you're going to do the same thing on the other one. 10 to the power of negative 3.0 equals your H plus concentration. Now you're going to take your higher number, which is actually the negative 2.8, over the lower one, negative 3.0, and you're going to divide the two answers, or you can actually subtract the powers and then go 10 to the power of it if you want to. Doesn't save you really any time, so we can do it exactly how we see it. Okay, and you should get 1.58 times. To the nearest tenth would be 1.6 times more acidic. And that's it for our applications of exponential and logarithmic.